So at this point, I had a working prototype, a Telegram bot pulling stories from a Google Sheet. It worked, but it had a serious problem. Google Sheets isn't a database, it's slow. It can't handle multiple users, and it couldn't do the one thing I actually needed: generate stories using AI on demand. So, if I wanted to build an iOS app, one that generates stories, manages user accounts, tracks reading progress, I needed a real backend. I had never built any of this before. So, in this video, I'm showing you what I built, how it works, and the challenges I ran into. So, let's go. Let me show you exactly what Google Sheets couldn't do. With the Telegram bot, I had maybe 10 stories in a Google Sheet. Fine for testing, but for an app, I needed first thing was story generation on demand. I needed to generate new stories using AI whenever I wanted to add content. Google Sheets can't call an AI model. Next was user accounts. Multiple users, each with their own child profiles. Google Sheets can't handle authentication. Third thing was reading progress. The app needs to remember which stories each kid has read, the completion percentage, achievements. Google Sheet can't track per user data efficiently. Then the next was speed. Google Sheets API can take 2 to 3 seconds per request. A proper database responds in milliseconds. And the last is scale. What happens if 100 people use the app at once? In this case, Google Sheets would fall apart. So I needed three things: a database, a server, and a hosting service. Now let's talk about the tech stack I used to build this app. I had no idea what stack to use. I researched popular options and Cloud Code helped me narrow it down. My main requirements was that everything had a free tier to start. For database, I chose MongoDB because it stores data as JSON-like documents. It's beginner friendly and has a free cloud hosting option through MongoDB Atlas. For the server, I chose Node.js with Express. Node.js is JavaScript running on a server instead of a browser. Express is the framework that makes building APIs straightforward. For hosting, I chose Render. It is free tier, beginner friendly, and automatically deploys from GitHub. And for media storage, I used Cloudinary. This is where all the AI generated images and audio files live. It's also free to start. So that's the complete stack for the project: MongoDB plus Node.js with Express, Render, and Cloudinary. Honestly, I had no idea what this was before this project, but it made sense once I understood it. So before I talk about building the backend, let me show you what this backend ended up becoming, because it grew far beyond what I originally planned. What started as a simple server that just served stories became a full platform with AI story generation pipeline, user authentication with email, Google, and Apple sign-in, child profile management, reading progress tracking, achievement system, favorites, category management, and then it was audio generation and storage and image upload and management. The iOS app talks to this backend through API endpoints. Then the backend talks to MongoDB for data storage, Gemini AI for content generation, and Cloudinary for storing images and audio files. Let me walk you through each piece. MongoDB Atlas is a cloud-hosted database. You don't need any local installation. Just sign up, create a database online, and Atlas gives you a connection URL. That URL goes into your environment variables, and your backend connects to the database automatically. I have 4 collections in the database. First is stories. This is the main content. Each stories has a title category, all the scenes with text and images and audio, a cover image, and a moral at the end. Second is users. One document per parent account. It stores their email, how they sign in, and all their child profiles are embedded right inside the same document. Then third is categories. It consists of story categories like adventure, bedtime, friendship, and so on. Each category has its own background image and icon stored in Cloudinary. The category backgrounds and icons are also AI generated. So when a new category is created, Gemini generates the artwork automatically. And the last is user activity. Every interaction gets logged here, like views, favorites, reading progress, and achievements. This is how the app knows what each child has read and how far they got. The story schema is the most complex. Each scene has its own images array and its own audio files array. The cover page has images and audio. The moral has audio. It's deeply nested, and that complexity caused challenges I will talk about later. Now let's talk about API endpoints. Endpoints are just URLs the iOS app calls to communicate with the backend. Each one does a specific job. Most requests include either an API key or a login token in the header. This is how the backend knows the request is coming from the legitimate app. The backend has endpoints grouped into three areas. First is story endpoints. The most important one is /generate story. This is what I call to add new stories to the app. It triggers the entire AI story generation pipeline. The next is user endpoints, which includes registration, login, all three auth methods, and profile management. And the last one is activity endpoints. This is how the app tracks reading progress, favorites, and achievements. Now let's talk about the AI story generation pipeline. This is the most important part of the backend and the most complex. So when I want to add a new story to the app, I send a request to /generate story, and here is exactly what happens. First is stage 1, which is generate the story text. The request includes age range like minimum and maximum, story theme, difficulty level, a user prompt to guide the story idea, and a language, which is English by default for now. Then the backend calls Gemini 2.5 Pro model. It returns a structured JSON response with the title, all in paragraphs, a character sheet describing how the characters look, a generation seed number, and the moral. The character sheet and seed are crucial. I will explain why in a moment. Then the stage 2 is generate the cover image. With the story text ready, the backend calls Gemini 2.0 Flash model to generate the cover illustration. The prompt includes the story title, character descriptions from the character sheet, and the generation seed. The next is stage 3, which is generate scene images. For each scene in the story, images get generated. Each image prompt includes the scene text, character sheet, and the same generation seed from stage 1. The next is stage 4. All images get uploaded to Cloudinary. Cover in one folder, scene images in another. Cloudinary returns permanent URLs. The next is stage 5. In this, the complete story like text, Cloudinary image URLs, metadata gets saved to MongoDB. And the last is stage 6, which is audio generation. After the story is saved, audio generation starts for the title, each scene, and the moral. Each piece of text is sent to Gemini 2.5 Pro TTS model with the auto-no voice. The audio comes back as raw PCM format and gets converted to AAC using FFmpeg before uploading to Cloudinary. Important point to note here is that the audio generation happens after the story is saved. So if audio generation fails, the story still exists. It just won't have narration. This keeps the pipeline from completely breaking if the TTS API has issues. We will go much deeper into how this actually works in the next story generation video. Now let's talk about achieving character consistency for all the images. One of the biggest challenges with AI image generation is that the same character looks different in every image. So when you're using a chat interface like ChatGPT or Google's AI Studio, the AI remembers context from earlier messages. But in an API pipeline, every single image generation call starts fresh. There is no memory of previous calls. The solution for achieving character consistency across all the images was character sheets and generation seeds. Now let's talk about the character sheet. When the story text is generated, I also generate a detailed visual description of every character like height, skin color, eye color, clothing, details, or any distinguished feature. This description gets included in every single image prompt. The next is generation seed, which includes a unique number from 1 to 1 million assigned to its story. This seed is also included in every image prompt, asking the model to maintain visual consistency. Using the character sheet and generation seed has brought this character consistency from maybe 40% to around 80 to 90%. It's not perfect. You will still occasionally see inconsistencies even in main characters, but now it is better than before. Now let's talk about the authentication system. The app supports three login methods: email password, Google sign in, and Apple sign in. Each one works completely differently on the backend. First is email and password. So when you create an account, your password gets encrypted with bcrypt before storing in our database. The app never saves your actual password, just the encrypted version. So when you log in, it encrypts what you typed and compares it to what's stored. When you register, a verification email gets sent with a link. You have to click it, verify your email ID before you can log in. The next is Google Sign In. When you sign in through Google Sign In, Google's own login page, Google verifies your identity. The app then sends your Google ID and email to our backend, which creates or finds your existing account. Then the last is Apple Sign In. It has the same flow. You go through Apple's login, Apple verifies your identity. Then the app sends your details to our backend, which creates or finds your account. Apple requires this as a mandatory option for any app that offers third-party login. So if we have Google, we must have Apple too. Users can also delete their account entirely from the app through Profile tab by using Delete Account option. It removes all their data, profiles, and reading history permanently from the backend. After you log in, the backend sends back a JWT token. JWT stands for JSON Web Token, basically a secure digital pass that proves you are logged in. It gets stored in the iPhone's keychain. Every time the app talks to the backend after that, like saving reading progress, updating profiles, this token gets included automatically in the request. And that's how the backend knows it's you. I will go deeper into how authentication actually works into a separate video. Now let's talk about child profiles and data management. This part was interesting to design. The app supports multiple child profiles under one parent account. Each child profile stores name, age, gender, avatar, theme color, reading level, language, and narration preferences. For now, all stories are in English, but in future, I am planning to add multilingual support as well. The backend also uses the child's profile to filter stories automatically. So when a child opens a story category, the backend only returns stories that match their age and reading level. So a 2-year-old never sees stories meant for 6-year-olds. The key thing is when a child reads the story, the reading progress gets stored with their specific profile ID. So Emma's progress and Liam's progress are completely separate even though they are under the same parent account. And the progress tracking goes deeper. Every story has one of 3 states per child: not started, in progress, or completed. So suppose Emma read a story A until scene 2 out of 5, then switch to story B. And then when she comes back to story A, the app opens it at scene 2, not scene 1 or 3. Every page turn saves her progress automatically. This shows up directly in the app. When you open a story category, say adventure, the stories are split into beginner, intermediate, and advanced tabs. Each tab shows how many the child has completed, like 1 of 4 completed. Each story card shows its state: green for completed and orange with percentage as continue if they left in half read. There's even a hide completed toggle to clear out finished stories and focus on what's left. Children can also favorite stories using the heart button while reading. Favorites are stored in the backend, and saving 10 favorites is what unlocks the Story Lover achievement badge. All of this is handled by the progress endpoint on the backend. It breaks everything down by difficulty level. So you can see Emma completed 4 beginner stories, has 2 in progress, and hasn't touched 6. Same for intermediate and advanced. Reading streaks are tracked per child profile. The backend checks their activity history and calculates how many consecutive days they have read. If you miss a day, streak resets to 0. Achievements unlock automatically when the summary is requested. The backend calculates this from the activity history every time. Achievement badges include first story, beginner master, intermediate master, advanced master, reading champion, reading streak, which is 7 consecutive days, story explorer, which is reading from 3 different categories, Then we have Speed Reader, which is 3 stories in one day. And the last is Story Lover, which you get when you bookmark or favorite 10 stories. You can see this reading progress and badges in the profile tab. Now let's talk about images and audio storage. All media like story images, cover images, audio files, category backgrounds lives on Cloudinary. Everything is organized into 5 folders: scene illustrations, cover images, narration audio, category backgrounds, and category icons. The audio pipeline is interesting. Gemini TTS returns audio in PCM format, which is a raw uncompressed audio. Then it's converted to AAC using FM MPEG before uploading. This keeps file sizes small for mobile. When a story gets deleted, the backend first deletes all its Cloudinary assets, like every scene image, cover image, and audio file before removing the MongoDB document. Images and audio are stored as different resources type in Cloudinary, like images as image and audio as video. So the deletion logic handles both. I deployed the backend on render. Every time I push a commit to GitHub, render automatically picks it up. For a minute or two, the server goes down while it deploys, then comes back online, and you can watch the whole thing in the deployment logs in real time. Environment variables like the MongoDB connection string, Gemini API key, and Cloudinary credentials are stored in render's dashboard, never in the code. One thing to know about render's free tier is that if the server gets no requests for 15 minutes, it spins down. The next request takes around 30 to 60 seconds to wake it up. So this is an ideal for user experience. I started on the free tier and later upgraded to $7 per month, which keeps the server always running. Now let's talk about the challenges I faced while working on backend. Challenge 1 was the nested data structure. As I mentioned earlier, the story data structure ended up being way more nested than I initially thought. Think about it. A story has a cover page with its own image and audio. Then each scene has its own image and its own audio narration. Then the moral at the end has audio too. So when I was designing this, I had to sit and think, okay, how do I actually organize all of this in the database so it makes sense? Deleting a story was the same thing. You can't just delete the MongoDB document and call it done. So with Claude's help, I built a delete endpoint. You pass in one story ID which is available on MongoDB, and it automatically collects every image and audio files across all those nested layers, deletes them from Cloudinary, then removes the story from MongoDB. Just one curl command and everything gone. Then second challenge was audio pipeline failures. The audio generation pipeline is the most fragile part. Sometimes Gemini TTS hits rate limits. Sometimes the conversion fails. Early on when audio failed, I would just delete the whole story and regenerate it. What I didn't realize at that time was that the architecture handles it perfectly. Stories get saved first, audio generates after. So if audio fails, the story still exists without narration. There is even a slash story audio endpoint to retry just the audio without regenerating the whole story. Then the third challenge is API design growth. The backend started simple, 2 endpoints, 1 model. It grew as the iOS app needed more features, like reading progress, then achievements, then incremental story fetching, then category management with AI metadata, then audio generation. Each feature added endpoints and complexity. The server.js file grew to nearly 3000 lines. It's not an ideal architecture. In an ideal architecture, this would be split into separate files, one for story routes, one for user routes, one for auth routes. But for an indie project, it works. Then the next challenge was image consistency. Already covered earlier, but it deserves a mention here. Getting the same character to look consistent across 5 to 6 scenes was harder than I expected. I tried different approaches, experimented a lot with prompt engineering, and eventually the character sheet plus seed number combination worked. It went from maybe 40% consistency to around 80 to 90%. Not perfect, but good enough for kids. So there were definitely other smaller problems along the way. Things I don't even remember now, but these were the main ones that took real time and thought to figure out. Now let's talk about what I learned while building the backend. First thing is, building a backend from scratch when you have never done it before is genuinely hard. Not because the concepts are impossible, but because there are so many layers: database, server, authentication, file storage, external APIs, deployment, and a lot. Every layer has its own problems. Second thing is, start simple, add complexity gradually. The first version of the backend had just two endpoints. I added features one at a time as the iOS app needed them. Trying to build everything at once would have been very overwhelming. Then the next is importance of architecture decisions. The decisions you make early stick with you. How I structured the database at the start made certain things easy and other things hard later. Think about how you will use the data before deciding how to store it. Then the next is external APIs failure. Like Gemini, Cloudinary, MongoDB, Atlas all have outages, rate limits, and unexpected behaviors. Don't assume they will always work. Building the audio generation to happen after the story is saved so a failure doesn't break everything. That decision saved me multiple times. Then the next lesson is never hard code sensitive information. API keys, passwords, database credentials, always store them in a .env file, never directly in the code. Never push them to GitHub. Then the next is test deployment early. Things that work perfectly on your local machine can break when you deploy. I ran into certain issues I didn't even expect. So deploy early, don't wait until everything is built. So that's the backend for GiggleTales. From a Google Sheet to a full production server with AI generation, authentication, reading progress, and everything in between. In the next video, I'm diving deep into the AI story generation, how the prompts work, how I achieved character consistency, and what the complete Gemini pipeline looks like in detail. So if you guys have any questions about the backend architecture, make sure to drop them in the comment section below. Thank you guys for watching. See you in the next one. Until then, bye-bye.